Stanford University.
Okay, well, welcome to the first reading of 8.871. Our guest lecturer today is Professor Shoucheng Zhang, one of the young physicists I most admire. He's a professor at Stanford. He's one of the leaders of a new generation of condensed matter theorists who really work in the style of Dirac, who look for beautiful equations and find their reflection in the real world. His work has been, in recent years, leading to spectacular results. He's giving a seminar tomorrow, a lunchtime seminar, in room 4331, in which he'll announce or demonstrate methods for finding monopoles, axions, Majorana fermions, all these things we've dreamed about in ordinary substances. Well, not so ordinary, special substances, very cleverly designed and analyzed. Well, okay, that's what I have to say. They're the usual biographical facts, but I think I'll not bore you with those, but let Shoucheng show you his stuff.
Okay, thank you very much. Thank you very much, Frank. A great honor for me to come here and talk to you at MIT. As you will see throughout the talk, a lot of the beautiful work, some few theoretical work done here at MIT many years ago greatly inspired this set of recent discoveries. So there has been some recent development in the field of condensed matter physics. And really, like what Frank said, it connects to many branches of physics, especially ideas coming out of field theory. And now it goes under the general name of topological insulators and superconductors. And I'd like to share with you these ideas and the experiments which seems to confirm some aspects of it. So in the subject of condensed matter physics, we search for new states of matter. So just like in particle physics or in chemistry more than 100 years ago, it was the search of basic elements which defined the golden age of chemistry. And 50 years ago, it was the discovery of new elementary particles, which defined the field of particle physics. But in the subject of condensed matter physics, there are no new particles to discover it. And we're dealing with the same electrons and protons and so on. But what we're trying to find are new states of matter and trying to find ways to classify them, to predict them, and to understand them in their complete systematic way. So one way to understand and classify states of matter is through the principle of the broken symmetry. So we say a crystal is different from other things because even though the elementary atoms interact with each other in a translationally invariant way, inside, once a crystal is formed, the translational symmetry is broken. Now inside a magnet, the rotational symmetry is broken. And in a superconductor, some slightly more subtle symmetry called the gauge symmetry is spontaneously broken. And that has been the condensed matter physics in the past many years, ever since Landau formulated this principle of the broken symmetry. So then in the 80s came the discovery of the quantum Hall effect. So it is a two-dimensional system of semiconductor interfaces subjected to a high magnetic field. And when you measure the Hall conductance, you find that it's always some integer multiples of some elementary quantum E squared over h, which in resistance is something like 26 kilovolts. So soon after Laughlin's beautiful gauge argument, Fowler and co-worker first recognized that's maybe the first time where the idea of topology of electronic states came into condensed matter physics. They basically showed that the quantized Hall conductance is actually a topological invariant. So these days, when we say topological states of matter, we actually mean something very precise. that there are actually physical quantities which are topological invariants. And here the connection is most direct. It turns out these plateaus, each one of them is characterized by a topological invariant called the first Chen number. But that was formulated in momentum space, and it can only be defined when you have single particle states or a non-interacting system. So later on, we formulated the topological field theory, and that's based on Chen-Simon's topological field theory, which is naturally defined in the 2+1 dimensional system. And the Chen-Simon's term, of course, was invented by a mathematician, but was first introduced to physics by Desert, Jacqueff, and Templeton. And it turns out that this is exactly the topological description of the quantum Hall state with these quantized Hall conductance here in the front. And many topological consequences can be derived from it. Now you notice that such a formulation does not require a single particle picture, it's more general. And when you put quantum Hall fluids into topologically non-trivial manifolds, Professor Shoucheng Zhang here pointed out that it leads to ground state degeneracy, and that's another higher sense of topology. But very recently, a new class has been discovered. And the key difference, I will summarize only in one sense, is that whereas quantum Hall effect breaks time reversal symmetry, the new class of two-dimensional and three-dimensional topological insulator does not break time reversal symmetry. So it does not require application of magnetic field. So the first time it was predicted for a real system was our paper in 2006. I will also go a bit more into the history of leading towards that. But this is the first time when it's predicted and was very soon experimentally realized in a mercury telluride quantum well. And very soon after that, the progress in this field has been tremendous, almost happening in a very fast pace. Fu and Ken predicted three-dimensional topological insulating business antimony very soon was experimentally observed. And in just last year, we predicted that bismuth telluride, bismuth selenide are topological insulators, and almost concurrently, experimental observation of it was announced by Zahid Hassan's group. Your graduate student, your postdoc here, David Shea, played an instrumental role in both of these experimental observations, and also the photo emission work at Stanford. And it has been recognized that this is a new state of quantum matter, and that's the story I'd like to share with you today. So in order to understand quantum Hall effect and the quantum spin Hall effect, there's basically only two equations you need to remember. The first equation says 2 equals to 1 plus 1, and the second equation says 4 equals to 2 plus 2. And when you really think about it, it's really the essence of both of these states. Okay? So let me try to explain to you why. Now suppose you live in a one-dimensional world, and let's for the moment even forget about the spin degree of freedom. Then you have only two basic degree of freedom, right? If you live in one-dimensional world, you can move forward or you can move backward. These are the two one-dimensional degree of freedom. So if you have something like a Fermi gas and you feel it up to some point, then you only have two Fermi points. And the first one describes a forward mover, and the second one describes a backward mover. Okay? So now if you live in such a one-dimensional world and you march along and you suddenly hit something, then you will be marching backwards. So this kind of wire will always have resistance. So not something universal. The idea of quantum Hall effect is to, very much like we do with traffic lanes, right? You separate these two counter-moving degree of freedom widely spaced in the extra dimension. So the quantum Hall effect is two-dimension. The conduction only happens on one dimension, but you use the two-dimensionality to separate these two one-dimensional channels spatially, okay? So if you have a two-dimensional sample with a finite width, then in quantum Hall effect, the forward mover lives on the upper edge, and the backward mover lives on the lower edge. So such a situation can only be realized when you break time reversal symmetry. Obviously, if you live here, you only see things moving forward, so it's the time reversal symmetry is broken. And in the case of quantum Hall effect, that time reversal symmetry breaking is due to the external magnetic field. It defines a sense of rotation by the right-handed rule or the left-handed rule. Okay? So now once you have 2 equals to 1 plus 1, then you have a magic thing that happens. Because then when you hit the impurity, there's no way to go back. Because you have to jump all the way across the sample and then move back. And that probability is exponentially suppressed. So when you hit the impurity, the electron will simply go around and keep on marching forward. So it's like you have an army of soldiers which only know how to move forward and never know how to retreat, right? So then there's no dissipation in this channel. So this is kind of the magic of quantum Hall effect. So it's really not a joke to say that 2 equals to 1 plus 1 is really kind of the key essence. And you will, throughout the talk, you will find that it's always this kind of a fractionalized idea that some degree of freedom gets spatially separated. It's kind of the fundamental underlying idea behind everything. Okay? So the way we do physics to make progress is simply to generalize, right? If you say somebody do 2 equals to 1 plus 1, what's the next thing for you to do? You do 4 equals to 2 plus 2. Okay? So first of all, where does the 4 come from? So in a one-dimensional system, when you deal with electrons, you really don't have 2, you have 4, right? Because you have spin up, spin down, and then you can move forward or backward. So you have 4 elementary degree of freedom. So if you have a simple parabolic band of the electrons, you have red upspin and blue downspin, and if you linearize near the Fermi momenta, you indeed get 4 degrees of freedom, up, down, forward, and backward, 2 times 2 equals to 4. Okay? So now, it turns out there are many ways to separate 4 equals to 2 plus 2. Okay? So a simple way, for example, if you have spin up, forward, and spin down, also forward, and that would also be a way to write 4 equals to 2 plus 2. But there will be a somewhat of a trivial generalization of the quantum Hall effect, because such a state will still break time reversal symmetry. And it is, in fact, nothing but a nu equals to 2 quantum Hall effect. A more interesting way is to separate and write the equation of 4 equals 2 plus 2 in a time reversal invariant way. Okay? So now what is that? So you say upspin forward and downspin backwards in the upper edge, and downspin forward and upspin backward in the lower edge. So now if you reverse the arrow of time, of course forward mover becomes backward mover, but upspin also becomes downspin. So such a state can be realized without any external magnetic fields and does not require time reversal symmetry. Okay? So such a kind of state was independently proposed by King and Lee in a model without any lambda levels, and in a model with lambda levels by Bernard and myself. But now, when you look at this picture a little bit more closely, you say, wait a minute, there's a serious problem with this picture. Okay? You say here, you say the things are moving dissipationlessly because there's no way to move back. But here, look, if I have a forward mover and I have a backward mover, I draw them separately. That's only because I cannot really draw them on top of each other. But if it's time reversal invariant, they're really sitting on top of each other, right? So if you hit an impurity, why can't I just turn back? Right? So this is the question you will have. So now when you learn quantum mechanics, you will ask to swallow many, many peculiar things. Now one thing which is absolutely remarkable about quantum mechanics is a deeply mysterious and yet profound fact. And that has to do with the fact that if you have integral spin and if you rotate by 2 pi, the wave function goes back to itself. But if you have a half integer spin and if you rotate by 2 pi, the wave function goes to the negative of itself. Okay? So this is the most peculiar fact about quantum mechanics of half integer spin. And nobody really understands why. But it turns out exactly this fact of quantum mechanics which leads to the protection of the quantum spin Hall effect. Okay? So first of all, it leads to a fact that if you reverse the arrow of time, normally you would say if I first let the clock move forward, but then I turn the clock back, everything's back to itself. But this is not true in quantum mechanics if you deal with half integer spins, right? So if you have spin up, if you reverse the arrow of time, it becomes spin down. If you reverse the arrow of time again, it becomes spin up again. But in the whole process, the spin has been rotated by 2 pi. So if you multiply the time reversal operator twice, you get -1, not +1. So this is another way of saying this deeply mysterious fact about quantum mechanics. In a time reversal invariant system, if you square the time reversal operator, it gives you -1. Okay? And that leads to many, many interesting facts, and in particular leads to the Kramer's theorem, which says that all states have to form doubly degenerate representations. And it has actually, for solid-state physicists, it has been used in a very important way for Anderson's theory. So now let's remember this deeply mysterious fact about quantum mechanics, the fact that you rotate spin by 2 pi give you -1. It turns out that's exactly the reason why the quantum spin Hall state is protected. So let's pick an example in daily life. So in optics or in camera, and sometimes in sunglasses, we know something called anti-reflective coating. So what is that? You basically have a thin film, it has 2 surfaces. Then when light hits and reflects back, it of course can be reflected by the first surface, and then it can also be reflected by the second surface. So if I choose the thickness of the film in such a way that it's commensurate with the wavelength of the light, I can construct it in such a way, the film in such a way, that both reflected lights interfere with each other destructively. Okay? So then there's no reflection, and the light will completely go through. Okay? So this is the basic principle of anti-reflective coating. So now let's go to the edge state of the quantum spin Hall effect. So we say that on one edge you have both upspin and downspin, but upspin is moving forward and downspin is moving backward. So what if you have this upspin moving happily forward and then it hits the impurity? Let's assume that the impurity is a non-magnetic impurity, so it does not break time reversal symmetry. But the impurity can have spin-orbit coupling, so it can in principle scatter the spin backwards. But if you scatter the forward-moving particle backwards, it has to rotate the spin at the same time, because the only channel that's moving backwards has the opposite spin. So in the process of doing so, the spin has to rotate by pi. Okay? But this is not the only possible path. For every clockwise turn around the impurity, there's also a counterclockwise turn if the time reversal symmetry is there. So if it rotates, if it goes around the impurity in a counterclockwise fashion, then the electron spin has to rotate by -pi. Okay? So there's 2 ways of being reflected. And if it's time reversal invariant system, the amplitude is always identically the same. But in the whole process, there's a difference between these 2, and the difference is that in the process of the electron spin has been rotated by 2 pi. But rotating the electron spin by 2 pi gives you always a -1. That's why these 2 paths exactly interfere with each other destructively, no matter as long as time reversal symmetry is there. So this idea is that this kind of protection is different from these. It's a similar concept. It's a destructive interference. But this happens all the time. Here you need to, it's not robust if the surface is rough. You have to choose the film thickness in an appropriate way and so on and so forth. So now you really see that, I hope next time we teach quantum mechanics, this will be given as an example. This deeply mysterious fact that you rotate spin by 2 pi give you -1 exactly leads to a destructive interference between these 2 possible ways of turning. So therefore, there's no way for the electron to turn back. So this quantum spin Hall edge is protected. So another way to say, of course, this is kind of a real space semi-classical picture. So if you look at quantum mechanics, you have energy bands, and if you have an insulator, you have a conduction band, and you have a valence band. So we actually, in solid-state physics, learned many times already about the fact that you can have surface states occurring inside the energy band. So in energy space, they live inside the energy band, and that's why when you solve momentum, you always have to get some I somewhere, and that means it's exponentially localized at the boundary. So it's very much like the evanescent waves in optics, okay? But these kind of, so then we say, what do we mean by topology? With topology, we basically try to do some smooth distortion. We say whether this picture can be smoothly distorted back to this picture. And usually it can be done because this kind of degeneracy is accidental. If you cut the surface slightly differently off and so on, you remove the degeneracy. Once you remove the degeneracy, you can remove even further, and then you say that this group of state is just like the valence state, and that group of state is like the conduction state, and there's no fundamental difference between these and that. Okay. So now let's look at the energy band diagram of the quantum spin Hall state, the proposed quantum spin Hall state. You have a conduction band, you have a valence band, but let's look at near the edge of one side. Then you have an upspin red, which is propagating forward, so it has a positive group velocity, so it's always monotonically increasing, and then the backward mover, which is the opposite spin, A spin you don't need to talk about in a sharply defined sense, but the sense of Cramer's doublet is sharply defined. The fact that these two are opposite is sharply defined. Whether exactly the spin direction is pointing doesn't matter that much. So then they cross at one point, and that's a time reversal invariant point at k equals to 0 or k equals to pi. So in this case, at this crossing point, it satisfies the Cramer's theorem. So throughout this lecture, you see that the central idea is t squared equals to -1. Rotating spin by 2 pi give you -1. That leads to t squared equals to -1. And very simply from quantum mechanics, we learned that every state has to form a doubly degenerate representation. So this satisfies the Cramer's theorem. So now if I add disorder, I miscut the thing, do a lot of violence to the system, as long as you don't break time reversal symmetry, Cramer's theorem has to be valid. So then if you can shift the dispersion in different ways, but this degenerate point cannot be removed. You cannot open up a gap here. Otherwise you will violate Cramer's theorem, and as long as you have a time reversal invariant case, you shouldn't. And that's why there's a fundamental distinction between this quantum spin Hall insulator and the ordinary insulator. Okay. So this is now quite exciting, right? So in condensed matter physics, we look for these new states of matter. It looks like just listening to these arguments, you see there's something very deep behind it. So now we have to do this nasty job of translating topology into quantum chemistry. We have to find a real material, okay? So actually the story of that discovery is really quite interesting, and it's inspired the results derived at MIT by a young PhD student, Redfish, who was a student of Roman Jacqui. So people tried different things. In graphene, it was proven not to work. There's a new paper finished just by the postdocs. But also we proposed something for strained gallium arsenide, but it looks like also not so realistic. So for a while it was very disappointing. But one day somebody came to my office and showed me a beautiful diagram. It's like a periodic table of all semiconductors. Okay. So they plotted in a two-dimensional diagram of energy gap versus lattice constant. So you can see for semiconductor engineers, it's extremely important, right? So suppose somebody wants to build a laser, a blue laser, or a red laser, because they can immediately translate by the Einstein-Planck formula the energy gap into a color. It's even nicely color-coded. They immediately know which element to pick. Now they also always try to stack things up in a sandwich form. So they go vertically, right? So you can put this stuff together because their lattice constant roughly match. Okay. So then when I looked at this periodic table of semiconductors, suddenly I noticed something. That there's absolute zero of energy. Okay. So energy is not only a positive number. Sometimes it can be a negative number. Okay. And there's basically only one semiconductor which does that. And that's called mercury telluride. Okay. So now why did I pay attention to such a negative gap? Because I was a graduate student in field theory. Okay, when I was learning field theory, I learned about these beautiful results coming out of MIT from Redfish. So he was studying under the advice of Roman Jacqui, Dirac model with the mass, and he integrated out the Dirac fermion and get the effective Chern-Simons term. But he found the result that the Chern-Simons coefficient only depends on the sign of the mass. So we knew that if the mass of the Dirac fermion changes, something very strange has to happen to the Chern-Simons term. And we know Chern-Simons term is roughly related to quantum Hall effects and so on and so forth. So that's basically the moment where it clicked. And then we identified mercury telluride to be the right material for realizing quantum spin Hall effect. And that's the story I'm going to tell you. So what exactly do we mean by a negative gap, and what do we mean by advanced structures? So you don't need to be a solid-state physicist, as any elementary knowledge of quantum mechanics will be sufficient. Okay? So after you solve the hydrogen atom, you know there are S levels and P levels. Okay? But then when you go a little bit more advanced in quantum mechanics, you know something called spin-orbit coupling. Namely, the P level under the spin-orbit coupling, P level has L equals to 1. It can couple to S equals to 1/2 of the electron spin. So it splits, and in hydrogen atom, this is nothing but the fine structure of the hydrogen atom. But the splitting gets larger and larger when you go to heavy elements. It scales roughly like z squared. So it splits into p3 half and p1 half. And the energy level diagram, the band structure of most semiconductors, you only need to understand that much about quantum mechanics. You simply put all the S level together, it forms a conduction band. You simply put all the P level together, it forms a valence band, and so on. Okay? So now I already gave you the hint, right? So the splitting gets larger and larger when you go to heavy elements. Okay? So what can happen? What can happen is an extreme situation that when you go into mercury telluride, mercury is already very, very heavy. So then the spin-orbit splitting of the P level overwhelms the original level difference between S and P. So the P3 half jumps above the S level, and the P1 half is still staying in the middle. Okay? So now in order to define the sign of the gap, you need a convention, right? So usually people take the convention of S minus P. But then you will see that mercury telluride is reversed. And so that's the reason why mercury telluride kind of has a negative mass. Okay? So now let's understand why negative mass is important. So let's build a very, so first of all, it tells you that, so basically if you put mercury telluride as a sandwich, mercury telluride is like the cheese, and cadmium telluride is like the bread sandwich in between. Then it depends on the thickness, right? Because cadmium telluride is normal, mercury telluride has this inversion. So somewhere, as the thickness of the cheese is getting thicker and thicker, somewhere there has to be a transition, right? Because in the limit when this is very thin, we know the S level lies above P level. When this is very thick, the P level has to lie above S level. So somewhere there has to be a transition. And if you do some simple calculation, you find this is around 6 nanometers. Okay? So now let's build a very simple model to understand it. So basically you only need 4 levels to consider. If you look at the S orbital, it can be spin up, spin down. If you look at the P orbital, you only need to consider the maximally spin-orbit coupled level. So if you have spin up, you have P plus IP, that has angular momentum LZ equals to 1, that adds up maximally to S equals to 1 half. If you pick spin down, you have angular momentum, maximal angular momentum of LZ equals to -1, which is P minus IP. Okay, so you look at simple hopping between these atomic orbitals, but you again don't need to understand any solid-state physics. If you know something basic about symmetry principle, you will immediately be able to write down what's the Hamiltonian. So of course, along the diagonal element, it's like the overlap between S and P with P, and that's pretty normal. But except there's a number which describes the level difference between S and P. And that's very important because we know a sign change occurs somewhere. But interestingly, when you look at the off-diagonal matrix element, namely S orbital jumps into the P plus IP orbital in the neighboring atom. Now because S and P have the opposite parity, it cannot couple when the crystal momentum is equals to 0. You have to take an operator which also breaks parity, okay? And that is the combination Kx minus Iky, or the opposite, right? So this is sometimes in solid-state physics how Dirac structure can arise. So Schrödinger equation always goes like k squared. But if you look at this overlap between orbitals, between S and P, they cannot couple when k is equals to 0, right? They can only couple when k is linear. So you get immediately a linear coupling between the S and P orbitals, and that's kind of the important thing. So that's why when you look at this is only in the upspin block, upspin S and P, and downspin S and P, right? But when you look at the limit when the momentum is very small, it roughly looks like the Dirac equation in 2 plus 1 dimension. And that's kind of how we originally hit upon this idea that if in mercury telluride there's a change of the sign of the mass, somehow something important must be happening when this level crossing is happening. So now, without referring to these field theoretical results, we can very simply, if you just take this very simple model, okay, and the change of the sign of mass is basically the relative sign between the level difference between S and P measured with respect to the quadratic band curvature of the model. Actually, this term is actually quite important. So simple Dirac equation. And it goes a little bit beyond. So if you put this model on a two-dimensional system, you can solve, it's a very simple model to solve. You apply periodic boundary condition along x direction, you have finite boundary around the y direction, and if somewhere inside the system, the mass changes its sign to s going below the p level. Now outside, you can either take the vacuum, but actually conceptually it's simpler to think that it's simply a thinner mercury telluride, which has a positive mass. So then in this case, the sample boundary looks like a domain wall, right? So along this direction, you are simply solving a one-dimensional Dirac equation. So it's going like mass going from positive to negative, and then negative again going to positive. And that's again celebrated MIT result, Jakif, Rabi, Soliton. So this is just a one-dimensional model of the Dirac equation. If the mass changes sign, you will get bound state. But you get one bound state for every momentum kx, okay? So when you change the momentum kx, this bound state can shift in their energy, and that's what gives rise to the dispersion relation. So this mysterious fact, or this wonderful gift by nature to us, that there's this element, mercury, this semiconductor, mercury telluride, which in a very precise sense has a negative mass, or there's a band inversion that happens at some critical thickness, is the realization of the quantum spin Hall effect. And when you really think about it deep down to, it's very simple. And it's exactly the idea of 4 equals to 2 plus 2. So soliton is a fractionalization phenomenon. So this 4 degree of freedom gets spatially separated in 2 and 2. And that's kind of the key essence. So now it turns out that mercury telluride quantum well is relatively more difficult to make compared to gallium arsenide. But there's one very, very good group in Germany, Würzburg, the same place where quantum Hall effect was originally discovered by a young graduate student by the name of Klaus von Klitzing at that university. But after that, they went into the so-called 2-6 semiconductor, mercury telluride. I think for more application-oriented, mercury telluride is a very good infrared detector. So more applied work, but they built a very good MBE machine, and they could fabricate this quantum well better than anyone else. They have reached a mobility about 1 million, which is comparable to gallium arsenide already. But the theoretical prediction is kind of very remarkable. Only then we could convince them to actually carry out this experiment. Namely, we say you grow the quantum well, and first you grow it with 5 nanometer in thickness, and then you grow it in 7 nanometer in thickness. And when they apply a gate to tune going from the conduction band to valence band by changing the gate voltage or shifting the chemical potential, so in the middle, if it's an ordinary trivial insulator, you will have 0 conductance. But if you get into this non-trivial insulator, simply by changing the width of the quantum well structure, which they can very easily tune by the growth of mercury telluride layer, then beyond a certain critical thickness, you will have one pair of edge states. And so here, if you raise the chemical potential a little bit on the left electrode over the right electrode, you will see that you will populate the red channel more on the upper edge, and you will populate the blue channel more on the lower edge. So in altogether, you will have access channel, 2 more access channels, and that, according to simple quantum mechanics, will predict a conductance of 2 squared over h. And that's what was experimentally seen. And furthermore, they have varied the width of that bar. And if it's Ohm's law conduction, we know the ohmic conductance will scale with the width. If you have more cross-section, you have more way for electron to flow. But here, not so, because no matter how wide you separate it, it's not conducting in the bulk anyhow. You're only conducting at the edge. So that's why for all different devices with different ladder width, it always saturates at 2e squared over h. And more remarkable, actually, this was also discussed with Patrick. I remember at a meeting in Hong Kong where he made some very insightful suggestion. And basically, in order to really prove the edge state conduction, you should look for non-local transport. So if you then now have made a device of the form of letter H, it's a recent science paper, and if you pass a current from 1 to 4, normally if it's only conduction, most of the current will simply go from 1 to 4. But if it's edge state conduction, it can only flow like this. And then you can, very far away, in the other arm of the H, measure a voltage between 2 and 3. But furthermore, these numbers are all rational numbers, which you can simply deduce from edge state conduction picture, and the experimental data falls very close to the theoretical prediction. So now let me quickly switch gear. So from this two-dimensional topological insulator to the three-dimensional topological insulator, and I will first talk about the material and then a little bit more about the general theory. So if you can look at the edge state of this two-dimensional case, you form this crossing point is like a massless Dirac point. Okay, so you say, well, you get one pair. So this is one Dirac fermion upstairs and another Dirac fermion downstairs, and this is a kind of an interesting structure. Then, if you generalize to a three-dimensional structure, you will try to find some three-dimensional material whose surface ideally only have one Dirac fermion in 2 dimensions, so you will form something like a Dirac cone. So it turns out the material which has this property is in bismuth 2, selenium 3. Okay? So it's a little bit complicated material, but basically it forms a quintuple layer. So it has 5 layer, 5 layer, 5 layers stacked together. And that has a center of inversion around the selenium layer in the middle. Then you have 2 bismuth layer and 2 selenium layer. So in the case of mercury telluride, I informed you that the important electronic orbitals are s orbitals and p orbitals, which have the opposite parity, and somehow due to the spin-orbit coupling, inversion happen. So this looks like a complicated material, but again, very, very simple to understand. It's basic electronic structure. So we understand the electronic structure in different phases, worrying about big number first, and then worry about small numbers. So the first, like a very simple thing we learned about quantum mechanics is if you have the center of inversion layer, you like to form bonding and anti-bonding states. So you first take, so only relevant orbitals are p orbitals, and you take simply the bonding and anti-bonding orbitals of the p orbitals. The next thing, you look at crystal field splitting, because the layers, it's a 2-dimensional layer structure, x and y are different from z. So it turns out closest to the Fermi level, it is the bonding orbital of the bismuth and the anti-bonding orbital of the selenium p orbital, which are closest to the Fermi level, and they have the opposite parity. So opposite parity is again very important because it leads to Dirac structure. It leads to Dirac Hamiltonian, which linear in momentum k, as I just argued earlier. But as you tune the spin-orbit coupling in this material, there's a level crossing that happens, and after the level crossing, similar kind of banding. So the mechanism in this material is almost identical to that in mercury telluride. So now you again write down a 4x4 model just for PZ bonding orbital will spin up, PZ anti-bonding orbital will spin down, and so on. And along the diagonal element, you will have this level difference between these 2 orbitals. But all the off-diagonal matrix element has to be linear in K, starting linearly in K, and that's because they have the opposite parity, and to form actually a beautiful kind of Dirac structure. So once this level crossing happened, or band inversion happened, you find that there will be a surface state. And the surface state will be a single Dirac cone. Okay? So if you look at the surface, it has a 2-dimensional crystal momentum, and you will have a single Dirac cone living on the surface. And whose importance I will discuss just a little bit later. And by now it's not so strange to find kind of Dirac fermion-like structure in solid states, and in fact graphene has a Dirac structure. But it turns out that in graphene has 4 Dirac cones. It has 2 equivalent momentum points and has spin up, spin down. But the surface of bismuth selenide has only 1 Dirac cone, and that's kind of a remarkable fact. And again, you see this theme of 2 equals to 1 plus 1, 4 equals to 2 plus 4 occurring over and over again. It's always somehow the surface or the edge has less than what is usually present in their respective dimension. So when you did, so our colleagues at Institute of Physics, Chinese Academy of Sciences, did first principle calculations. And it turns out that there's a family of 4 related materials, and 3 of them actually spin-orbit coupling is strong enough that the band inverts. So the way to recognize, and if you later want to find some new material, which may be a topological insulator. There's a very, very simple recipe to look for it. So basically, when you look at this kind of material, it has a valence conduction band and a valence band. But this material, spin-orbit coupling, is not strong enough. They're getting very close, but it hasn't inverted yet. But once they get so close that they hit each other, after the collision, there's some wreckage of collision. So after the collision, usually these things are no longer a direct band gap semiconductors. So after the collision, basically you have always a double hump kind of structure. So these bulk bands and the surface band are all kind of related. It's quite easy to recognize. And in the case of bismuth selenide, you indeed have kind of a single Dirac column. So first experiment was done by Zahid Hassan's group at Princeton. Your postdoc here, David Shea, was also important participants. We have done experiments on bismuth tellurium in Xiaoxin's photo emission group, and the data is a little bit has finer resolution. That's the only reason I choose to present it here. So because the crystal has a hexagonal structure, if they did a photo emission experiment, they actually initially, as grown material, the material was grown by Ian Fisher's group at Stanford. They see actually this beautiful surface state which forming a hexagon, but in the middle there's still a bulk state. But when they add some sufficient dopant, the bulk state finally went away. Basically, they're shifting the Fermi level around. And now when they look at the dispersion, it's really kind of a textbook Dirac fermion, as you can see in this beautiful example. So this recent theoretical development of topological insulators is very, very good news for a lot of the experimentalists, because a lot of the experimental techniques are surface sensitive, like uppers and STM. And when they study something like high temperature superconductors, after giving a very nice talk, they always have to make an apology. Oh, I worked very, very hard, but I cannot completely get rid of the surface state. But if you hear a talk on topological insulator by experimentalists, they will say, oh, I worked very, very hard, but still a little bit hard to get rid of the bulk states. Because the surface state is the golden thing, gold mine that they are looking for. So, and a lot of STM results are also kind of coming up. So there's also material science aspect of it, and we have a very nice office arrangement at Stanford where everybody's together. And one day I bumped into my colleague, Yi Fei, and he's an expert in growing nanoribbons, and he has already grown nanoribbons because it's a layered structure, very much like graphene. So a lot of the graphene work you can do also in this kind of system. And after growing these nanoribbons, they have done a beautiful experiment seeing the von-Aharonov oscillation. So if you put a flux through this nanoribbon, and if the surface state conduction dominates, basically anytime they enclose the integer number of flux, you will see some periodic oscillation of the conductance peak. So now let me come to kind of so you say this word topological insulator, what exactly does it mean? What exactly does topology mean in the case of topological insulator? We basically now have two definitions of topological insulator. One is in terms of the band structure, and that is more like the generalization of the work by Thouless and co-workers, defining a Z2 topological invariant, starting with the work of Kane, Fu, and Wall, and Balance. So this definition is very useful because if you have a band structure, you can immediately plug in and calculate. It turns out they're divided in two classes. They either give you 0 or give you 1, and 1 means it's topologically non-trivial. But it does have some drawbacks. One is that this picture relies on a single particle picture. Okay? Whereas if you really want to define a new state of matter, at least maybe hard to calculate, but at least the definition has to be generally valid. And you also like to see a greater structure of which universality classes, how does it relate to previous works of Chen numbers, Chen-Simons term, and so on and so forth. So it turns out there's a more general definition of topological insulator, starting with topological field theory. And Frank Wilczek, even back in the 80s, people were studying axion physics and theta vacuum in particle physics. This kind of term was already introduced. And even at that time, Frank has said that, wow, this is such a beautiful mathematical structure. It must be occurring somewhere in nature, even in things like solid state. So now let me give you a general introduction of this idea. So if you have a solid insulator where both electric field and magnetic field will be well defined, then basically the solid electromagnetic response is completely defined by the dielectrical constant and the magnetic permeability as the coefficient of the Maxwell term. Okay? But in the general philosophy of writing down the long wavelength effective action, you will say, why don't we write down the term E dot B? And when you read Jackson, I think this kind of quantity was even discussed. But there was some good reason why people didn't discuss such a term, because we know electric field, even though it's a Lorentz invariant, the electric is something called a pseudo-scalar, because the electric field is even at a time reversal and the magnetic field is odd in the time reversal. So E dot B will be odd in the time reversal. You would naively say such a term is only allowed when you break time reversal symmetry. Okay? But what we find is that such a term actually is allowed even for a time reversal invariant system if you apply periodic boundary condition. Okay? But only for two possible values. Only so you can write down this coefficient universally expressed in terms of the fine structure constant E squared over H bar C with a coefficient theta. But when theta equals to 0, it's time reversal invariant. But for a periodic system, even for theta equals to pi, it's time reversal invariant. So now I will not go into the proof because this is a general colloquium, but let me just give you an analog you can immediately understand. So suppose I take a ring and spread a flux through it. For a generic value of flux, time reversal symmetry is broken. If you go around once and go in the time reverse path, you get two different phases. But when the flux is equals to pi, then you go around in clockwise fashion, you get phase vector of pi. Go anti-clockwise fashion, you get phase vector of minus pi, but minus pi and the pi are the same in a periodic system. So this is kind of the reason why that when this coefficient theta equal to pi in a periodic system, it also respects time reversal symmetry. So therefore, it gives you the most general definition of what's a topological insulator. A topological insulator is described by such a topological term. Why is a topological term? I will also explain. But with a universally quantized number. So you can view theta as some kind of phenomenological description of the material. But unlike epsilon and mu, theta can only take two values. So that's kind of the reason why it's a topological invariant. So now why it's a topological invariant is a little bit not obvious when you look at E dot B. But we know E dot B is not fundamental. E and B are not fundamental. So you first write E dot B in the covariant notation. And it turns out Maxwell action is F mu nu downstairs times F mu nu upstairs. So in order to write down a Maxwell term, you need a metric tensor. So Maxwell term has to depend on the geometry. And that's why light is bent in a gravitational field. But when you write E dot B, it's epsilon F times F dual. And they're contracted just by the epsilon tensor, nothing else. So even if you're writing a curved space-time, it will not depend on the metric. So that's why it's a topological term. So so this is all undergraduate level E and F, okay? But then you try to write E and B in terms of A, right? We were told in quantum mechanics that we shouldn't deal with E and B. In quantum mechanics, you should deal with A. But when you write in terms of A, you immediately find FF dual is actually a total derivative, okay? So it's a total derivative of the Chern-Simons term. Okay, so that again is always a recurring theme in topological physics. Somehow there's a relationship between bulk and surface. So this theta can really be interpreted as some kind of a surface term. And when you pick theta equals to pi, because the Chern-Simons coefficient tells you roughly about the quantized Hall conductance on the surface, and that theta equals to pi will give you a Hall conductance of 1/2 E squared over H. Now what's the interpretation of that? So if you take a topological insulator on the surface, let's say bismuth selenite, has a single Dirac cone. Now such thing, we call it a topological insulator, but it's not really an insulator, right? Because it conducts on the surface. You can make a true insulator if you break the time reversal on the surface, for example, by coating it with a thin magnetic layer. So then the Dirac point applies a mass, it has a finite mass. But if you have if you have a single Dirac cone and a mass gap opened up, and you are breaking the time reversal only on the surface, then it will induce a quantized Hall conductance of 1/2 E squared over H. And that again is in reference to Reddish's result from MIT. And that kind of physics has been seen recently in graphene. And in graphene, when they measure the quantum Hall effect, they measure it's always occurring in step of 2 E squared over H. But they expressed the number 2 in terms of 4 times 1/2. And they say that because there are 4 Dirac cones, the more natural unit is 4 E squared over H. So basically it tells you that a single Dirac cone, once time reversal symmetry is broken, immediately gives you 1/2. So the theta equals to pi is exactly measuring the number of Dirac cones on the surface modulo 2. And that's why it's a Z2 classification. So there's a more general theory of, in terms of the universality class, this picture I will show tomorrow. And there are a whole host of experiments, but maybe the most striking one is that of the magnetic monopole. So when you go back to high school physics, if you put a charge above some surface, in high school physics we learned that we will induce image charge, right? So now if you have a surface of a topological insulator, which by itself is not yet insulating, but if you put a thin magnetic film, it will be really truly insulating. But then on the surface, you will have 1/2 of a quantum Hall effect. So in this case, if you put an electric charge above the surface, it will generate circulating persistent current on the surface, which in turn generates a magnetic field. And the magnetic field is exactly the same as that of an image magnetic monopole. So the good news for the students here is that if you know how to solve Maxwell equation, you solve Maxwell equation with the inclusion of this new term, you can predict many, many experiments in this field. All it takes is just solving the Maxwell equation in the presence of E dot B. Okay? And so very recently, there has been some interesting paper posted on the net that there's even a deeper symmetry called SL2Z symmetry in the presence of theta term. And that's again something that Frank worked on and pointed out very early on. And that's, and also coming back to the whole history of anyhow, when Frank first thought about the idea of fractional statistics, I think his picture was having an electron, but in his own words, attached to some fictitious flux tube. So when you exchange 2 of them, the electron will see the fictitious flux tube of the other, and it picks up a Born-Aronoff phase and makes fractional statistics. Now, of course, I was a student and reading such a paper, how on earth will make a fictitious flux tube to electrons. This turns out to be an exact implementation of this idea of fictitious flux. Because then every electron induces a magnetic monopole. And that magnetic monopole is image. It always follows the electron. So when you interchange 2 of them, the electron will see the monopole flux, and this electron will see the other monopole flux. So when you interchange them, they will exactly reproduce the fractional statistics, or the operation of attaching a fictitious flux to the electron. And that can also be experimentally seen. So I'm coming to the end of my talk. Unfortunately, we don't have that much time left, but I would like to tell you that there's kind of a more general structure. And I will also tell you tomorrow that as long as you're interested in insulator, the news is basically there's nothing more. That there's only these 2 classes. And basically, the quantum Hall effect is related to the first Chern universal topological class. Quantum spin Hall and 3D topological insulators are all results of this second Chern class. And mathematicians have categorized them, so there's nothing more you can do. And, but there is something you can do, and that's by going to the superconductors. So the analogy is very precise, that if you have a insulator that has a gap, so if you can turn the insulating gap of the insulator into a superconducting gap, so then you get a very analogous picture. So if you break time reversal and form a state, so the simplest way to think about is something like spinless electrons paired into P plus IP state, then you will have a full pairing gap in the bulk. But on the edge, you will have chiral edge states. But it's not just chiral, because the superconductor breaks particle whole number conservation modulo 2. So you will have only the particle branch, but not the whole branch. And that's called the Majorana fermion. Okay? So Majorana fermion was first introduced again in particle physics And I guess Mr. Majorana thought neutrino may be a Majorana fermion. I think they were also trying to get rid of this negative C problem of Dirac fermion. But the superconductor or chiral superconductor is kind of the most natural implementation of it. But for a long, long time, before the excitement about time reversal invariant topological insulator, people always thought that in order to get anything topological, you need to break time reversal. And that's why some experimentalists even thought they're synonymous of each other. They find time reversal symmetry, they immediately thought they discovered something topological. But the lesson we have learned is that you don't need breaking of time reversal symmetry. So there must be a partner of the quantum spin Hall state, which is kind of what we call a helical superconductor, which also has counterpropagating states, but again, they're Majorana. And the gaplessness of the Majorana fermion is protected again by time reversal symmetry. So there are a lot of interesting work in this direction now, but the most surprising thing is that the model, if you take spin up paired into P plus IP, spin down paired into P minus IP, that Hamiltonian is exactly identical into the Hamiltonian of a two-dimensional topological insulator describing mercury telluride. Only the basis, the form of the Hamiltonian is the same, only the basis is different. In the case of mercury telluride, what you have is the s orbital and p orbital. But what you have in the superconductor is basically the Nambu doubling of the electron degree of freedom. You write C and C dagger together. So even in a one-band model, you can have this 4x4 matrix structure. But when you go to the three-dimensional case, you have helium-3b phase. And when you write down the Hamiltonian for the helium-3b phase, it's identical, term by term, to the three-dimensional topological insulator of business selenite, if you just reinterpret the basis. So now, because the experimentalists have already detected the Dirac cone on the three-dimensional topological insulator business selenite, it must imply that helium-3 surface is non-trivial. And on the surface of helium-3b, you don't have a Dirac cone, but you have a Majorana cone. Okay? So at this moment, I will again pause and to really, so when I first introduced this idea of 2 equals to 1 plus 1, 4 equals to 2 plus 2, you think it's really trivializing this recent discovery, but this is the key essence. So somehow when we discover a deeper and deeper topological state, basically every time you're taking half the degree of freedom, right? So if you take 2 degrees of freedom in one dimension, put half upstairs, half downstairs, you achieve something very profound to write 2 equals to 1 plus 1. So when you think a single Dirac cone is already the most elementary thing you can do, a single Dirac cone, and graphene has 4, you say it's already a big deal. You have only a single Dirac cone. But yet, there's another way to half the degree of freedom, and that's going from Dirac to Majorana. And after that, I really don't know if you can do anything further. So this state, again, is a great gift by nature. Helium-3b wasn't really realized until quite more recently, that it is a topologically non-trivial state. And recently we have proposed an experiment to detect the non-trivial surface state. Basically, if you have a helium-3 liquid, you can shoot in an electron, and the electron digs a bubble inside the helium. And you can shift the height of that electron bubble simply by electrostatic capacitor. And so when you move to the surface, you will see faster nuclear spin relaxation as compared to the bulk, because the bulk is gapped and the surface is gapless. So basically, this is the story that we, in condensed matter, we are trying to see these different states. And for a while, there was, it looks like Landau is always right. All the states you can find satisfy this broken symmetry principle. But now we have this quantum spin Hall state, and of course the first came the quantum Hall effect, but now we have the quantum spin Hall state and topological insulators, and they really have this remarkable physical property, which is a direct reflection of the topological invariance they possess. Thank you.
You can take us to questions.
Yeah.
We all have a broken topological symmetry.
Yeah.
We have this E dot B term.
Yeah.
I wonder for this topological symmetry breaking insulator, do you have similar picture like?
Yeah. So this case E dot B. Yeah, E dot B is only broken on the surface. In the time reversal invariant topological insulator, the bulk is, so theta has to be exactly equals to pi for the bulk topological insulator.
But what I try to say, if the bulk,
yeah. So actually, there's a realization of that. So basically, it's related to the axion angle theta. And if you look at this crystal bismuth selenide, you have two bismuth sides. And when you put in transition metal elements into it, it can actually order antiferromagnetically within the unit cell. And in this case, actually, not only will have a general value of theta, which can kind of give more general definition of the sense of topological insulator, even in the time reversal symmetry class, but as well we'll talk tomorrow, that these also give you a dynamical axiom. So the amplitude fluctuation of that it is exactly follows the equation of the axiom. Yeah.
Oh, yeah.
Roman, yeah.
Wonderful.
Composite. Yeah.
Is it actually an arbitrary medium or is it just?
Yeah, that's a very, very good question. Yeah, that's an excellent question. Yeah. Yeah. So first, it's for general material, it's an arbitrary axiom, anion, and the anion angle is actually very close to fermion in the statistics. But we only realized very, very recently that if you have these two dielectrical materials, but if they're close to a quantum phase transition to a ferroelectric or to a kind of becoming ferromagnetic, some of the dielectrical constant of magnetic permeability will diverge, and near that point, they will behave exactly like semion. So they can actually have a very large statistical angle measured with respect to the fermionic angle.
I have a question about the quantum spin Hall effect.
Yeah.
So the argument that scattering clockwise and anti-clockwise cancels is
Yeah.
on time reversal.
Yeah.
But quantum Hall effect is normally in the presence of a magnetic field.
Yeah. So that's the two different classes, right? There's the quantum Hall class, and there you only need a classical picture because everybody is just marching forward. The quantum spin Hall class is guaranteed by the presence of time reversal symmetry.
But in a magnetic field, we don't.
No, we don't. Quantum spin Hall, the key essence is you don't have a magnetic field. You don't have. So these are the two important classes now: the T breaking class and T invariant class. Quantum spin Hall is the T invariant class, and that's protected. Quantum Hall is more robust. It's robust against anything. Quantum spin Hall effect is only robust against non-magnetic impurity. So the fact that T squared equals to -1 being a symmetry is a key essence.
I was wondering, for when you induce a monopole on the surface, is there another half of the monopole hiding?
And that's very, very far away. So whenever you talk about fractional charge in kinetic metaphysics or spin charge separation, of course everything is made out of the electron. The sense it's defined is that they can be separated arbitrarily far apart, like a soliton, anti-soliton, and that's the sense in which it's defined. Yeah.
So this doesn't help the people, but many could spend many man years looking for a free monopole.
But I would say that if you live on the surface, it's really no difference. If a free monopole exists, or if this surface monopole, this civilization that develops on the surface of topological insulators, which they will very happily announce that they discovered. Yeah, because for all practical matter, we could be living in some domain war, right? If a free monopole can be coming from some other direction. So there's a different level of, But the idea is that, I think that's also some point of view Frank is trying to discuss, is that the same mathematical structure, the ubiquitous presence in both high energy world and the elementary world really tell us that they must play a role in the building blocks of fundamental laws of nature. That's such an appealing structure in the Dirac style of phrasing this kind of approach.
Well, thank you very much.
For more, please visit us at stanford.edu.